Okay, good morning. So today is the last session. This is now the last session of the course, and yeah, so far, yeah, you have learned many options to how to go in optimizing your code and to make it faster running yeah, take advantage of GPUs and take advantage of multiple CPUs. And yeah, now you know how to bind to C, and you know how to compile Python code with Numba and with Python. And in this part here now, we're going to see how we can get the code we have and how we can scale it to multiple nodes. And with that, we will have a more complete way of using HPC resources. Okay, and one important things of today is that so we're going to see scaling, but scaling it has to be in general your last step of optimization, and so it's better to work with the things that you know so far, and so from yesterday and the day before, and to try to make your code as fast as possible with going with Numba or using the GPUs, or even if you have to write things in C. And then after that, when you're sure that your code is really using the hardware in a single node optimally, then is only when it's advised to scale. There are other reasons to scale, like you need more memory, and if you need more memory, well, there is not much you can do. You have to scale, but in general, you should follow this idea. No? Let's close something here that just open. Okay. Yeah, so the first thing before entering in the content, which is going to be, so we're going to for the parallel and the scaling. Sorry, for the scaling, we're going to see today Dask just as a preview. But before, we are going to make a small stop to see this a tool that we have at CSCS that is called IPython, that we're going to use today here to bring support of multiple nodes on the notebook. And so here I have a demo that I'm going to run it. You won't be able to run it with your kernel, but you don't really need to run it now. But yeah, it's just to showcase the example. So this tool is called IPython, and it's a magic command, same as you saw before, time it, and the profile things that we saw on Tuesday. So it's a magic command, and it is based on IPyParallel. And what it does is to run from the notebook. It will run an IPyParallel cluster. That this means some servers that they are going to be sitting in each of the nodes that we're going to run in, and the code that we're going to run in the notebook is going to be submitted to this cluster. Maybe I can increase the size a bit here. The code that we're going to run here is going to be submitted to this cluster, and like that, very easily we can create we can enable an MPI environment, and we can do communication between these servers, this cluster that we have launched. So to launch it, we use IPyCluster start -n2, and here we have two nodes. I selected two nodes, and so it takes a couple of seconds to run it. And that's it. So now we have the cluster. And if we do this, import socket and socket get host name, we are going to see the host name. We get two different host names. And notice that we are running this thing in a cell that is decorated with percent px. And this means that whatever is in the cell, in the whole content of the cell, is going to be submitted to the IPy parallel cluster. And it will run there. So for instance, now if we do socket get host name here, it's going to give us a name error because socket has never been imported on the notebook. It has been imported only on the cluster. Okay. So what is happening on the cluster is not has nothing to do with the notebook. The notebook doesn't know anything about what is happening on the cluster. Okay, so in this demo, what we're going to do is a very simple training of a model, and we're going to do some plots. And the training is going to happen in two GPUs, one GPU in each node. And at the end, we are going to do a plot to check that the path of the training is the same in both GPUs. Okay? So we import some stuff, and IPy parallel will show a progress bar when things are slow. So this something takes some time. So you can disable that with this px config minus progress after -1. So it never start the progress. Here you put the time after which the progress should start. If it takes more than 2 seconds, more than 5 seconds. So we put here -1, so it never started. It will never start. So now we don't have that. Here this means this is starting the MPI environment. And so now we have an MPI environment in the cluster. We have the option of running things in one of the nodes of the cluster by using -target0. We set where we're going to run it. If we want it in target 1, it's in the node 1 or a node 0. And if we put both, it's in both, and by default it will run in both nodes. Okay. And yeah, so here we regenerate some data. We convert the data to TensorFlow form. We create a model. This is something to get variables to plot later. And here in the two nodes, we are setting the initial position of the optimization to be in the same place. So they start from the same place, both nodes. And now we do the training. And the thing is that, so there will be 2 trainings running on each node, and there is a communication mechanism that is synchronizing them so they work together. And that's it. So with the training into nodes, and now we can do some plots. So the plots, we can do it in a single node. Otherwise, they will appear twice. So for instance, we plot here. We see the loss decreasing. So this is the value that is being optimized. So the minimization, and here we see that the line, this is a line that is fitting this data. This is what we train. And so it's important thing that for both the same things happen. So there is synchronization between both nodes. And if we put so only in 0, it will look like this. Okay. And finally, we can plot again the minimization over the parameter space of the model, and we see so it's the path that the minimization took, and it's the same for both of them because they are synchronized. And yeah, so same thing. We can plot in one of the nodes of the cluster, And at the end, when we finish our computations, we just stop.
Rafael, there are a couple of questions.
Yeah, thanks. Yeah. So I keep getting error when I import TensorFlow. Yes, sorry. I said at the beginning, this one you cannot run it because I didn't put TensorFlow on the kernel. I just want to show you the tool. The file is in. Sorry. So the file is in IPython 02 distributed. Okay. So don't the content of this is not really relevant. The important part is the IP cluster stat. And we have another example that you can run also if you have 2 GPUs, which, by the way, I wrote in the general channel in the morning that today we can ask in the launcher, we can put 2 nodes. But if you don't put 2 nodes, it doesn't matter. We are going to show this part now in multiple nodes, and most of the morning is going to be in a single node. So just if you want, just keep the notebook as you have it, and later I can tell you when to close it and open one with 2 nodes. Okay. Okay, and so this is exactly the same thing. And now what we are going to do is to use MPI for Pi. So MPI for Pi is well, is exactly what the title of the package means. It's a Python package that brings support of MPI to Python. And here we can open a file that we're going to use that is from the MPI repository. And you can see here that with MPI for Pi, you can import this MPI object, and you can do things like you would do normally in MPI in C or Fortran. You have access to ranks, you have access to the communication, to the whole communication infrastructure of MPI, and then all the functionalities like barrier and receive and send. And this package is very much used, but not too much by users of packages in general. It's more used by developers of big packages like, let's say, PyTorch, as a backend for communication. In practice, I don't think people write too much code like in this way unless you are doing a very sophisticated package. So that's because of that, we're not going to have a look to MPI for Pi in this course, and we chose to go better with Dask for the kind of use that we're going to do. Okay, but anyway, just quickly here we're going to in this demo we're going to get to measure the communication bandwidth between 2 GPUs. Okay, and so here it's a bit complicated code, but the idea is that we create 2 CuPy arrays, and one is empty and the other one has a range of numbers, and then they are going to be sent and received in different sizes or with different chunks of these arrays. And so this code is going to measure the bandwidth. And yeah, for that we use IPython just to showcase it again. And here we have to enable to set this environment to enable the direct GPU to GPU communication. So we do like this. And yeah, IPython. So IPython also, it has a help. And yeah, you can use it also in in your laptop, if you have MPI, by setting here -- launcher MPI run. And there is an option local that doesn't have MPI. It's just a set of workers that are disconnected. There is no communication between them. And in this case, for Dyn, we are using the default, which is srun. And yeah. So here you can set, so we have 2 nodes, but you can put more than one worker per node. So you put here, the number that you put here is going to be divided by slurm in 2 nodes. So if you put 12, it's going to be 6 and 6. If we put 11, it's going to be 5 and 6. So, but for this one, we need 2 nodes. And yeah, we start again a new cluster. Okay, it's done. And here we do this thing to avoid the IPy parallel progress bars. Here we check. We have the 2 nodes, fine. We import this file that I just showed you. We call the function that the file defines, and here we run for different message sizes. We get the bandwidth. Okay, so it's a very simple example. And this one you can use it for your own development. If you are working with something that requires multiple nodes, and yeah, it has already MPI or any kind of communication built in, you can use IPy Cluster Magic for your development if you use our Jupyter notebook. And then once it's ready, you create your script that you're going to run with srun in a you're going to submit to the queue with this batch. Then yeah, you just take the APC cluster parts out and all these PX, and the rest you can run it by, it would be equivalent to doing run your script, your batch. That's it. So I just quickly wanted to show you this tool, and then we can have a look now to VASP. I will restart the game. So I stop here. Yeah. Okay. So now the real content of today, we're going to have a look to Dask. And Dask is a library that is quite large, that brings parallel computing in Python. And how it does it is by enabling the construction of task graphs, computational graphs, and then that Dask will create, and then Dask will execute. And for the execution of this graph, we're going to see now in a minute how it happens. Dask will create workers and dynamically create threads or create more processes, depending the size of the graphs and the time that it is running. And built in on top of this graph capability, there is a part called Dask collections that is a reimplementation of NumPy arrays, pandas data frames, and something that is equivalent to a Python list. But in the backend, we'll have this graph kind of execution, and like that, the same code based on this graph can run from my laptop with a normal amount of RAM to a node like Dyn with a lot of RAM, to multiple nodes, exactly the same code. And we are going to see some examples on how to do that. So to start, the core part, the more base part of Dask is the Dask delay functionality. So Dask delay is a function that can be used to parallelize algorithms by creating computational graphs. And this is done like this. So let's say in this side here, regular Python code, you have these three functions, and you want x, which is a function of some argument, y, which is a function of another argument, and z, which is a function that depends of x and y. So if we run this one on normal Python code, this line will run, this line will run, and then at the end, this one will run. So at the runtime is going to be the sum of all these runtimes. With Dask, we do something different. We don't run anymore by lines. Instead, every line we declare and define a graph. So here it's exactly like this, but the function is wrapped by Dask delayed. So Dask delayed is wrapping the function, and then we pass the arguments of the function. And we say x equals Dask delayed of the function 1, y equals Dask delayed of the function 2, and z Dask delayed of the function 3, depending on x and y. So this one, it will run immediately. So it won't run the content of like this. So it won't call the function. It will just build a graph that looks like this. And here, since for x and y, the arguments do not depend on among them, Dask will do something like this: x and function 1, y function 2, so separated, and then z that comes later and depends on x and y will come like this as a dependency of the result of these two operations. And then func 3, it will give z. Okay, and once the Dask the graph is defined, we can run set.compute, and set.compute is going to go through the graph, and it will execute all the tasks. And the scheduling inside of the task inside of the graph is going to happen in a smart way that is done by Dask, and it will have things like these two. They can run in parallel since they don't depend on each other, and then this one, it will wait for these two results to be scheduled and execute. For instance, if this one takes more time than this one, this one, it knows it has to wait, so it won't fail because the result is not the variables are not yet computed. Okay, and then this x and y, they can be again, can be in your laptop, it can be in Dyn, can be in different computers, can be in a file system. So this one can be a function that is reading data, and this is function that is operating over data. And in that case, these functions here are going to only be declared as, okay, this function has to read something, and this function has to read something on file, and this one will get the output of these two, and only the reading and the whole thing, it will happen when set.compute is run. Okay, so this is a way of creating graphs. Also, you can do simply a list of functions, or sorry, of function calls that you want to add to the graph, and let Dask schedule it depending on the resources. Like for instance, here we create a list of functions, and then we say Dask.compute, and we pass all this list as one by one. That's we put the star, and Dask will compute it. For instance, if we have a machine that has only 2 CPUs, Dask will compute first these 2, and then when one of these finishes, and there is a space, there are resources on the computer for another task, it will execute the next one, and so on with depending the length of your graph. One important thing here is that the construction of this graph, as you can see here, more explicit, but also in the example we saw before, is done in Python. So it's just the construction of the graph is just Python code, and creating very large graphs is as a result is slow. So if you use thousands of tasks in your graph, the construction can be slow, can be very slow, and your code is going to have just a long just that time there, like using a single CPU constructing the graph. So in those cases, if you are in that situation, you should instead try to group functionalities and operations in a single node of the graph. Like for instance, if you have okay, let's say that you have 10 operations like this one. It's better to, instead of creating 10, well, 10 is fine, but let's go 1,000. Instead of creating 1,000 of this operation like this, maybe it's better if instead you have a larger function that is going to call 100 of them or 10 of them, and this larger function, the normal Python function, is the one you're going to delay. So this node of the graph is going to execute many of these things that otherwise would be nodes of the graph. Okay, because very large graphs can really take a lot of time. We can have we can try later if we have time. And that's it. So on top of this functionality of Dask delay, this second part of the Dask collection is built in, and there is Dask array, Dask bag, and Dask data frame. So the arrays implements a subset of Numpy API, but a very large subset, many operations. And these operations are re-implemented in blocked algorithms. So that means that a Dask array is going to be formed by small NumPy arrays, and the Dask array operations, functions, are going to operate over this set of blocks. Okay, and then the building of the graph and everything that we did by hand now in this example before is going to be done automatically internally inside of the array. And we're going to see examples and we're going to understand better how that works. So the same thing exists for Dask bag, that is like kind of a Python super list. So it's a list that the backend is based on this Dask delay, and there is also Dask data frame, which is equivalent to Dask array, but for pandas data frames. And the good thing of using these things is that, again, you can run it in your computer and you can run it in a big cluster. And also, since the execution of the graphs, so the execution of the operation is done through the graph, it is possible to do operations on data that is larger than what you have as your memory. Because the things are going to be executed as they are needed, depending on the resources. And we're going to have a look to that too. I see there are some questions. Sorry, this slides is the same slides that I shared on Tuesday, just a bit ahead of where we finished. There is another question, but we cannot see it. Yeah, that is a very good question. There is a question that Dask can build graphs over functions coming from CFFI, Nomba, and F2Py. And yes, so these functions here, or like in this case, Dask doesn't care what the function is, and Dask doesn't know anything about the content of this function. The Dask will just schedule and execute these functions within the graph. So here you can put everything that you have learned so far You can put number functions. You can even put GPU functions with CuPy. And yeah, just in the particular case of CuPy, there are there are two things. One, if you use normal Dask, as we're going to see today, since the memory of the GPU is in general way smaller than the RAM, at least in a supercomputer. That, for instance, here we have 64 gigabytes of RAM in the 9 GPU nodes and 16 gigabytes on the GPU. So since this memory is so small, you have to be careful with the amount of memory that Dask is using on the GPU. So you have to think in advance how much memory you will need. But yeah, you can use anything as a backend. As a backend, no, sorry, as a function, or here as in Dask array as a backend. Also, there is another solution that is implemented by NVIDIA that is called Rapids, that is more tuned towards machine learning. And they implement, so there are two main things. One is something that they call Dask local CUDA cluster. That so you create it, and this cluster you can set how to limit the memory of the the memory of the GPU is not exceeded, and it will do some optimizations like that to do not go over out of memory on the GPU. And also you can do things. It will do things like, if you go out of memory in the GPU, it will start transferring memory to the host. So there is this, and together with that, they have Dask data frame implementation like this one that they call QDF, which is CUDA data frame. And there is not such a thing for NumPy arrays. And yeah, this is called Rapids. We're not going to see it here because it's more like tuned to deep learning, and yeah, we want to keep it more like general. But sorry, deep learning or machine learning. But yeah, it's a solution. Okay, so now that we know the basic of Dask, we can come to we can come to Dask, to the Dask folder here. And let's open the first notebook. So this notebook is we're going to do we're going to reproduce this this thing that yeah, something like this that we saw here now, and we're going to see how it works. Okay, so here we import Dask and time to measure, and we have these two functions. This one gets a square of a number, and this one gets adds two numbers. And then I put a sleep inside just to measure time and see how much they take. Otherwise, it's going to be too fast. And an important thing is that sleep, if you remember from Tuesday, sleep is a pure Python function that does an OS call. And as a result, this function regarding the GIL, the global interpreter lock, is in a category called OS bound, IO bound, and that means that it is implemented opposite of the CPU bound. So this one will release the GIL before executing and acquire it after executing, which means this function can be run in multiple threads, can be run in parallel. Okay. Later today, we're going to see what happens when we have pure Python code that doesn't really release the GIL, and how we deal with it in Dask. Okay, we have these two functions. In normal Python, we run this one, and this is going to take 3 seconds. So it's 1 second, these two, So 1 second, 1 second, and 1 second, so 3 seconds. And now let's use Dask, and we build a computational graph. And just look here, this exits immediately. So here we just define the graph. Okay, so if we put set here, it's not a number, it's just delayed. And this thing here is the ID, they call it key that is just internal for Dask. The key of this offset inside of the graph. Okay, I think if we do Y, we will get something similar with a different ID. So now we can visualize it. And here this LR is only just to print in this direction instead of down. And here we see the same thing we saw before in the slide. So the square function, so it's executed here, and then it's passed to the add, and then the add gives the result. And at the end, we can do set compute, and only now the graph is going to be executed. Okay, and now we see that it takes 2 seconds and so 1 second less because the normal Python, because these 2 square operations, since they do not depend on each other, they can run in parallel. And the fact that time sleep releases the GIL means that they will run actually in really parallel in the threaded environment that Dask creates. So by default, Dask uses here I think it's called scheduler threads. Yeah, it uses scheduler threads. So it will use threads, but there is also possibility to use processes. To use processes and instead of threads, but the default is threads. And now we're not going to talk about it. We're going to have a look later in a case where this distinction will be relevant. And now I will give you 5 minutes. It's a very simple exercise. So to go with this through these examples here and apply something like this and construct graphs instead of the normal Python operations. So if you run this one, there is a range 10. So they will take around 10 seconds or something like that. So create graphs and let's discuss it later. And you can also visualize it as we did here. And the solutions are here. You can just run these cells and you will see the solution. Okay, let's come back at 46, 47, something like that. Okay, we can have now a look to the solutions. So here I put delayed on the square, and I put delayed also on the sum. Let's see, let's visualize and see what happens. So here we see this, so we see all the squares, and these squares, they can be executed in parallel in the threads, and then everything is going to be summed. So there is another option to do not put sum. So do not delay sum. So so this is a normal Python function, or if it is a non-Py function, when something is like this, the function may execute. So sorry, Dask may realize that it's being called by a Python or external function, and it may execute the graph. or may rearrange it in such a way that to adjust for this part. So in this case, we can see that the execution is going to happen like this. So if we go back to the top, to the bottom, we see that it's in a square, and then it's added to another square, and then we have another square here, and it's added to the rest of the squares. So and we have this line here that goes through the graph, and the other squares are being added, and this happens like this. I think we can do like this better. And this happened like this because the sum function sums sums in a list one by one. And you see, so this is the list, how it goes increasing. So the list, no, sorry, the summation, and the new squares are being added one by one. Okay, so this is one. So in the next one, we have a for loop and a sum. Let's see. Yeah, we do. Sorry, let me copy just this one that has the random alar. Oh, no, this one we don't need the. So we see similar to the other one before. We also have the option with the sum. And here, the last one, there is an if, and depending of a condition, it will execute a square or an add. And this one, if we visualize it, it will look like this. And you see that these operations here, the order here doesn't matter. They will happen. They are at the same level in the graph. So they will execute, it doesn't matter which one executed first. So if we run it many times, you see that the order here changes. Okay. So, and this is something very simple, but very powerful, and you can use it for anything you want, because this function can be anything. Just you have to pay attention if the function releases the GIL or not. Otherwise, you may end up running serially plus the overhead of the construction and scheduling of the graph operation. Okay, and okay, now we are going to move to another example. Yeah, we're going to move to another example. So now we're going to go back to our distance matrices, and we're going to try to do a city block distance matrix. Remember that in the city block metric, we cannot apply the trick that we did. So we're going to try to make a version based on Dask and CuPy. And here, let's go back to the notebook. Yeah, this one you're going to do it alone. And there is a solution here. So there is 02 exercise and 02 solution. And the idea is the following. So from the CF5, if you remember, we use this function from CuPy, which is a city block distance matrix implementation, to compare if the values of what we were computing were right, just as a reference. And now we're going to use it here because this function has, let me open just to show you better. Oops. This, I'm going to open top here. And we're going to be looking to CPU. This function is a fast function. It's implemented in CuPy and it's written in C. This C, I think, means C. It's not city block. So city block, you have to put it here. It's more general. Here you can put Euclidean, city block, and there are many options. But this is C implemented in C. But if we look here in the top, it's not multi-threaded. It uses a single thread, and we are timing it here to just to show that it's not multi-threaded. And for this data, 1200, it will take around 3 seconds. This is exactly the same calculation we did with CFFI, with the same number of points, so samples, and this is 3 seconds something. And in this notebook, let's try to we're going to get this value, this array here, and the idea is that let's try to we can split it, the array in chunks, right? So we are going to do 12 chunks, one per CPU, and that's why I put 12,000 here. So we're going to divide it in 12 chunks, and we are going to compute the distance with CDist between one of these chunks and the whole array. So it would be a CDist of X and XI, so a chunk of the array, a piece. And with Dask, we're going to use Dask delayed to run all these things in parallel, right? And then we put them together we concatenate them, and maybe we can speed up in comparison to this 3 seconds. Okay, so here I'm going to close this thing again to it doesn't close. Here this notebook is incomplete, so I put the code, and similar to before, you have to go and add the delays and visualizations. And so here in the cells, so the cell is empty. You have to fill them with the order that is here. Just before leaving you alone, so this is where we are doing the splitting. So we use NP split. So we split the 12,000 points in 12 chunks, right? And we iterate over it, and we compute and put inside of a list all the partial distances. So this is the full array and a chunk. So this one is what you have to delay. Then we concatenate it, and we finally get a final result. And yeah, that's it. So now please go through the notebook. I can give you until 10:10. And just fill in the orders and use the delay and see what happened. So remember, you can always open top like I did here. It's not opening now, the terminals, but so you cannot open the terminals. But maybe I think it's maybe Jupyter is a bit overloaded now. But later try again. If you manage to open it, you will see you can do top and see the processes. Okay. And okay, see you at 10:10. Okay, we're back. Okay, great, Tanya. So let's check the solution. Import. So this part we saw. This is the CDs. Just for reference, we use time to be faster. It's around 3 seconds. Sorry. So the first thing is we delayed CDist, and now if we visualize the partial distances, we get it's a set of independent tasks in the graph. And now the next step is we delay the concatenate. And so let's compute and get our value. That's it. So it gives us shape. Shape is fine. So let's visualize the whole thing. So it's the same, the task that we had, and now the concatenate, they just go through to the concatenate. So let's time it, and we use threads, and we can have a look here to the terminal if it wants to open now. Yeah, right. And so to top. And here we look at the CPU percentage. Yeah, it's here. And here we see using many GPUs. Someone is unmuted.
I went to two conference.
Thank you. So yeah, so let me run again. Here, yes, here we see that we are using our implementation is using multiple threads. And that's it. So now it takes around 1 second compared to 3 seconds. So let's have a bit more look in depth to our implementation. So if now, yes, first important, check that the result is the same as the referenced CDist. It's the same. And now let's time the partial distance only. So there is no concatenate. So you see it takes 400 milliseconds. So it's a bit over half of, under half of this, of the total time, which means that 60% of the time, so it's around 600 seconds, it will be just the concatenate, which is not very convenient. So this is something that we will have to improve in our function. But nevertheless, we went from 3 seconds of execution to 1 second. Of course, this is this number is for this size of data that we are using. Different size of data can give us different things. For instance, if we put something very small, like 1005, this probably is going to be worse than CDist, because we may end up. So this is very simple for CDist to do, even in a single thread, and our implementation has the overhead of creating graphs and scheduling the tasks. Okay, so similar. This is valid for also for this, similar as we did for NumPy. Let's try always different solutions, and so this one let's take it as it's only one solution with Dask. But yeah, nevertheless. So we saw this, and now if we want, we can put this the city block Dask. We can wrap it as we can pack it as a function, and if we give this to a user, the user doesn't know anything about graphs and doesn't have anything to do about the implementation. But someone using this function will give X and Y and the number of chunks in which the thing is going to be processed, that for different machines, probably different chunk sizes will give different benefits. And that's it. It's a good way of shipping this implementation. And here we check that our city block Dask gives the same result as CDist, and it's fine. So here, an important point of this notebook is the fact that CDist as a SciPy function, releases the GIL before executing. And thanks to that is that we can run it in using multiple threads. Otherwise, we would have to run it using processes. So if you know, processes and threads differ mainly in that the threads use shared memory. So all the threads, the different threads of execution, are going to use the same memory, while processes will copy their own memory. And because of this, scheduling processes may be more time consuming. And if we try here to put in processes, oh, I missed an S. So we can go to the top. What happened? Okay. Huh. So, okay, you can see here two processes. And this is very good because Dask schedule these processes dynamically, depending the size of how many tasks and how is composed the graph. Dask will try to find the better way to run it, so he can save in scheduling time and can organize better the resources. Okay, so here we see that this Python, there are two processes, and now there is one, but remember that timeit runs many times, so probably we shouldn't have used timeit here. But if we had a bigger, I don't know, a larger amount of chunks, we will see that Dask will be using more processes, and we are going to see this right after this notebook. To compute without concatenate, why? So there's a question: to compute without the concatenate, why should we use compute partial distances? I was using partial distances compute, but then so he's asking why we use compute and we pass partial distances instead of doing partial distances.compute. And so if you do partial distances.compute, it gives an attribute error list. Object has no attribute compute because so this thing finished just before replying to the question. You see now it took 13 seconds because we are using processes compared to 1 second with threads. So processes require a copying of memory and requiring a heavier there is a heavier overload in scheduling processes than threads. Okay, so the point that we were talking, that CDist releases the GIL and allows this optimization of the function by using threads is very important in this case. And this is something that you should always look when you use Dask, because sometimes it's not too obvious if the GIL is released or not. If it's code that you write, if you use Python or SciPy, of course, you can know they will release the GIL. But if you use a library from another package, if you are using something from a Python package that you don't know and it's a function, and you want to run it in a Dask graph, then you will have always to check and look at top and look at the times and check that for sure it is running in parallel if this is what you want. Okay, so going back to the compute versus the partial distance compute. So the thing is that so we define it here. Partial distances is just a list. It's not a graph compared to this one. So here at this point, this is just a list of operations. And if we want to run it with Dask, we want to execute it, we have to use dask.compute as and pass it. Otherwise, this list doesn't know anything about Dask. Okay. So here, when we pass it to the second, to concatenate, delete concatenate, now Dask will incorporate it like this in the graph. Otherwise, this is just a list. Okay. So now let's, before going to the break, let's see a quick example that is called threads versus processes. And it's going to be similar to the last analysis that we did here. Go back to the notebook, and the example is 6. Sorry, I skipped some numbers. So it's a 6. So you see, Jupyter is a bit slow. It took a couple of seconds to open it. So if something like that happens to you, just try, but let us know, and maybe try to wait a bit and see if it's better. Okay, so in this notebook, processes versus threads, we have this code. So if you remember, this is the bad implementation of the Euclidean distance matrix, so with loops. But I'm using it here just to make a point. And so this is obviously a bad implementation, but what I want here is pure Python code that takes a lot of time and that do not release the GIL. So we cannot use time, because time we know that releases the GIL, and we want Python code, pure Python code that doesn't release the GIL and takes time. So this is a very good choice. So we put here bad implementation. Bad implementation. So let's run it. We get some data. Yeah, so Jupyter is a bit slow. Let's try again. Okay, let's try to run it. Otherwise, we stop here, take the break, and we try to take care of the problem. But let's see if we can make it work. So let's time it and see how long this thing takes. How much? Sorry. Yeah, here we have it takes 2.5 seconds, and here we have a graph that is, again, is a list. It's just a list of operations. It's just the same thing repeated 12 times. Let's put 10. 10 times. Let's define it. It's immediate, and let's time it, and let's think now how long it's going to take. So based on the fact that Euclidean distance, one run with the same data, takes 2.5 seconds, let's see, try to guess before running how long is it going to take. Okay, we are measuring it. Let's see if we can get a notebook. So we see that we are using threads, but there are no multiple threads. There is only one thread. And this is to be expected, because we know already that pure Python code is going to be locked, and in multi-thread environment. So there is no way that we can run this in parallel using threads. So if we come here and we look, we have 26 seconds. So roughly 10 times. So we have 10 tasks. Roughly 10 times of top got a bit crazy. Okay. Book is stuck. So roughly 10 times. Okay. So now let's try with processes. and see how long it's going to take. So now processes, the difference is that each of them, so I want to show you here, but it's not happening. Each of them is running on a different process with a different memory. So the GIL has no impact in these things, since every process is independent and each will have their own GIL. And this is not something of multiple processes, is not something that of concern for the global interpreted log, since the memory is separated. There is no way that the memory is going to be corrupted by multiple threads. Okay, so we can run again here, and let's see how many processes Dask is going to create. Okay, top is not working. Okay, we see two processes. And yeah, this number, two processes, is just selected by Dask for performance reasons. And in the next slides, so in the next tutorial, we will see how we can select this number ourselves. And now you see that this 16 is not really, even if they can, the same of one, even if they could run all in parallel, but because of the overhead in scheduling all these processes, Dask decide to use two processes instead of one per task, even if there are resources, because it is at the end it should be more optimized. It should be better to do it in this way. Okay, so now, for instance, if we have more tasks, let's make here the double of number of tasks. So now we have 20 tasks. Okay, this one is fast. This is slow behavior is just because Jupyter is slow now. So we have our 20 tasks, and let's see what happens now with execution. We cannot see, but okay, yes. Now we have four processes doing the thing. So now, since there are more tasks, Dask decided to use four processes. And let's see how long it takes. 17. So before was 16, and now it's pretty much the same. Okay. So, and now the last test, let's comment all this. And now we have two. Again, this is just Jupyter. This should be fast. So if we run with threads, this should take around 5 seconds, because it's twice this. And with processes, let's see how long it takes. So the same thing. So in this case, even if we can run in parallel, if this thing can run in parallel, there is no advantage of using processes in this case, because we have so little tasks that the overhead in creating the processes or executing the graph through processes is just too large and doesn't give us any advantage. Okay, so here we can close. And yeah, if you have questions or something, so this is very important when you're writing your code with Dask, because as I said before, it's not obvious what the function that you're running is how it's going to behave in the graph. So do always these tests, threads, and see if it is actually running in threads, compare with processes, and try different arrangements. What I was saying before, now that at the beginning about the sizes of the graphs. So if we do this graph and we make it with 2,000, 5,000, a million tasks like this one, this is going to take a real long time, really long time, and in creating the graph, probably much more than the execution. And what I was saying before, that here we can see more, and now we understand more. In that case, if your graph gets too large, maybe it's a good idea to create a third function that exec Euclidean, and then in this function call this one many times. Okay, so this one, in this case, it doesn't make any sense to call this function anytime because it doesn't produce anything at the end, everything's lost. But imagine if this function is reading something or is doing something that persists, that you save it in disk. So instead of putting this one directly 1,000 times in a graph, it's better that you put this one 200 times in a graph, and pack the executions and the workload on a single node of the graph. Okay. Yeah, here now we can stop and we can take a break. So it's 33. Yeah, let's come back at 45. Let's come back at 50. Okay, let's come back at 10 to 11. Continue now with the second part of the session, which is going to be about Dask arrays. So Dask arrays belong to the second category of things of Dask has, the data collections. And Dask array, is one of them. And the Dask array implements the NumPy array, but as I said before, all the backend and everything is based on the Dask delay, on the graph execution, and all the algorithms, even if the API is the same, everything is implemented by blocks. So all the algorithms will be using blocks, and when you have a Dask array, it will be an array. It will look, you deal with it as an array, but in the backend it will be a set of NumPy arrays, something like this. These arrays can be anywhere. They can be in disk, can be an HDF5 file on disk. They can be in memory. They can be in remote machines. It doesn't matter. And because of this, because of the fact that the backend is based on block algorithms and the graph execution, for equal sizes, some operations in Dask can be slower than on NumPy. And we're going to have a look to that now. So here, as just to understand better what is happening, so we will see it's the same that we saw before, but let's consider this example that we have some data in disk here, and we want to do an operation that the operation itself requires more memory than what we have in our computer. And how Dask will approach this? So that will do something like this. It will read the memory. It will read the file, and then from it will take only some data that fits in memory. Like for instance, this three nodes here. It will compute them, get the value from them, and free all this memory. And now read this part, compute the next node of the array of the graph, and releases memory. And now at this point, the disk, everything can be released. The connection to the disk can be closed. And now there are only these 2 points of the array and the final, and the calculation is done. The memory is released here, and finally the memory can be released here and passed to wherever you're passing this value. And that's it. So this is what it's doing in the backend, and doing this kind of operation is how Dask manages to do operations that on memory that is larger than the system memory. So now let's go back to the notebook and run the 03 Dask arrays. Before I will close shut down all kernels. Okay. And I have two terminals here that I don't see, but they are running. All right. And let's come to the third notebook, Dask, 3 Dask arrays. So here we're going to see for the first time Dask array. So we import it like this, import Dask array as DA. And this one, it will behave very similar to a Numpy and how do you operate with it. So here we create a random. This is the legacy, let's say, way of creating random data. It's not like we did yesterday and the day before, but this one doesn't exist in Dask yet, the one we are using. So we use this one. And here we can write the chunks how we want them. So this array is going to occupy 30 megabytes, and each chunk is going to be around 2 megabytes. We'll have 16 chunks, 4 by 4, and each of 500 by 500. Okay. Another way is to use auto, which is the default. We can do like this. Yeah. And again, all these things similar to this one. This is just declaring the array. There is no calculation of the random numbers at this point. It's just Dask. So Jupyter that is a bit slowish today. But yeah. So when we use chunks automatic, instead of passing ourselves the chunk, Dask we will try to get sorry, there's a question I think is what I want to say. I will stop a second and read it. Can you quickly tell again how to decide what chunk size to choose? Yeah. So the chunk size is very important, and we are going to see in a bit why. So here I put only 500 just for visualization to show you the API. And here we let Dask to do it automatically, and it will use a chunk size, which you see here is 4,000 by 4,000. That will give you around 8 million. So he will choose this size such that the chunk which in the algorithm in the backend is going to be an NumPy array. The operations that you do with it, they are going to be in a size of NumPy that is not too small of an array, and it's not too big. The two cases are, if it is too big, it may happen that it won't fit in memory. And if it is too small, it will happen that the operations that you do in the array, let's say that you want the sum of all these values, or the sum in one direction, or the average of the whole thing. I'm sorry, I lost the idea. Yeah, if it is too small, what is going to happen is that doing the operation in one of the chunks by NumPy is going to be very fast. So if it is like this one, 500 by 500, this is going to be microseconds to get the average, or to get the sum of the whole thing in NumPy, and it is going to be more complicated to schedule this large amount of chunks, because each chunk is going to be a point in the graph, than executing the operation in the chunk itself. So what you're going to see is that most of the time is going to be wasted in scheduling the operation in the chunks than the work in the chunk itself. So as a summary, you have to find something in between. For something like getting the average, or that we're going to do now in a minute, I think it's better to leave it alone as Dask prefer. But in other cases, like the next tutorial, we will see that it's better if we specify the chunks as we want them. Okay. And a value, if you have to put the values, I would say something similar to what Dask would give you. Something that is in the range of the millions, between 1 and 10 millions in the size of the chunk. Okay, so in this case, 8 million is what Dask decide to do. And we're going to see in a minute, we're going to use the dashboard, and we are going to see what happens. We're going to visualize what is happening for different chunk sizes. But let's continue here. So if we do the mean, we're going to get the mean of this whole thing. This is also immediate. Again, it's Jupyter that is being slow today. And we can visualize what we are doing here. So here is very small, but maybe I can, yeah. So here we have random samples, all this. This is where the arrays is coming. So at this point, this random doesn't exist. They are going to be divided in these groups. So it's 1, 2, 3, 4, 5, 6 groups. I don't know, maybe I'm counting wrong. Yeah, 6 groups, and then all of them, they do operations, like sort of a pyramid of operations on them. And then the next part, there is mean, convene, partial, mean chunk. So it gets the mean of the chunk, convenes the mean of the partial parts, and combines again the mean of the partials, and at the end aggregates the whole thing. And if you can imagine, so if you put something small, I think this is going to take some time, but let's put something like 1,000 by 1,000. So now we have many chunks, right? So before, how many we had? Was 25, and now we have 400. So there is more scheduling involved in this operation. With the mean, I think I will regret this, but let's see. So now, yeah, he's complaining that the graph is too large, but now there is, you see, all the amount of operations that the graph has to do, and every single one of them, they have to be scheduled. So this one, we're going to measure them now, and this is going to take much more time than if we use a chunk size that gives us something more sensible in the rate of number of operations to be scheduled, so points in the graph, and size of the Numpy array. Okay, so this is the two values that you have to take in account. All right, so now here, so this one, yeah, we can compute. We have 2000, and the mean takes 523. If we put, well, we'll do it later. If we put smaller chunks, this is going to be slower. And let's compare this one to NumPy. So NumPy takes a bit more time than Dask. But now, if we go and do this thing, so let's go to slow to not get into slow. So this one I think is fine. It takes, it's faster. 400, and with small chunks, 421. Okay, so it doesn't seem to make too much of a difference for this amount. Let's go for a smaller. So here you see we have 1,000,000. So let's put smaller and see what happens. So now, yeah, now it's going to get it's going to be more way many more operations. Okay, I hope it doesn't take too long. And okay, so in the meanwhile, that when this is running, if well, I hope it doesn't take too long. So this operation is a simple operation. It's the mean. Oops. Where I was? Here. So you see, it is the same amount of data. It's exactly the same thing. It just takes a lot of time, and it's a very simple operation. 31 seconds compared to NumPy 2 seconds. So the chunk size is indeed, yeah, very important. So let's keep it like this. Now I guess it's Jupyter. Okay, so this graph you saw is not too complicated, but when you do an operation that has a complicated graph, like let's run this one in NumPy, is a dot. This is a matrix product, and so it's the same thing that I forgot to update this one. It's the same thing that doing this that we saw the other day. So if we do this one with Dask, again, this is declaration. This should be fast. And we do visualize. Now this graph is very complicated. And even if we choose, we don't have too much points here. If we choose a good chunk size, when with such a complicated graph with so many operations, there is a lot of scheduling. So these things can be may take a lot of time if you have a lot of data. So to show here, let's see if we go to 2000. Okay, so it's increasing. It says that this number, this chunk size is too small. So maybe we leave it to this. Let's see what it created. Okay. We do why now? We get it complicated. So now we have more data. This thing starts to be slow. And here, this is a dot product. So it's the same of matrix multiplication, but oh no, sorry, I got confused. Sorry, yeah, we have two matrices here. We can put, and for many points, it starts to get very, very slow. So in Dask, it's very important to understand these operations that are very complicated, which means complicated graphs, loss of movement of data, and loss of scheduling. That one maybe is not a good idea to do it directly in Dask graph. Dask arrays. Dask arrays, I think it's better to use it in operations that that are not that complicated, like getting so comparing data, getting averages of large amount of data, or getting maximums, these kind of things. But a matrix product in, for instance, in Dask can be very time consuming. Okay. So now that we saw Dask arrays, let's try something. I will reset the kernel. Let's try using IPython and create a Dask cluster by hand. I don't see this happening, but so IPython has the possibility to create a Dask clusters, passing the option -Dask. This one internally, it will create an IPyParallel cluster, but IPyParallel gives also support for Dask clusters. And like this, we can get a basic Dask cluster, and we can use it. So now I want it in a single node, but we can use it over multiple nodes. This thing is a bit slow. So let's see what happens. So this one that we are doing here, it will allow us to open the Dask dashboard. And in the dashboard with the diagnostics, we can have a better understanding of the scheduling and how things are happening. Invalid syntax. Yeah. Okay, so the cluster is almost ready, and now it creates this cell here that wasn't there, and it has the link to the scheduler file. So we do like this, and we see we have information on the scheduler. We have one worker because we pass -N1, and here this is dashboard, this link, but this link we cannot see it because it's not public from the compute node of Dyn to us. So we will use this one that is the same thing, but it's piped through a proxy that is here. So we can click here. Okay, so it takes some time, and there is some information that it gives, and now when it runs, we can look at it. We can see the task stream. We can see the bytes that the cluster is storing, and the progress of the tasks. And then we can look at the workers. So this is information now. The worker is not doing anything. And this is the same that we saw before. Information on the system. If we're using GPUs, information on the GPUs. There is information to profile your code. The graph, like I showed before in this scheme, but the real thing it shows here. And yeah, there are many things here. We go in info. We go outside with information about the Dask. So we're going to work mostly in this page, but there is a trick that we can do. So we can copy this link here, Control C, and come here to this thing that says Dask extension here. And I already have something. Sometimes you need to refresh it. And we put here, we make sure that we don't have any space around it because it's very sensitive to space. And we can use all these things that are here. So let's find what we want. So we want task stream. Okay, we lost it. So it's not showing now. Okay, sorry. Yeah, for some reason it's not working now. I guess because we are live. Good. Okay, now it's working. So yeah, I'm sorry. Today Jupyter is a bit slow. So we can put this one and we can put the progress. We can do like this. And now let's see different chunk sizes and see what happened. So here in task stream, this is time in the x-axis, and in y, it is the number of threads. So you have here all the threads, and here the time. So we have our things. So let's work with this one. Let me put the chunk size down so you see it. So let's do min, and now let's execute it. Y compute. So here we see the progress, and we see the time. So here it was very fast. We will see later something slower. But so this is the task that will correspond to the breakdown that happened here. And white means it's idle time. So this is time that the worker is not doing anything. It's just task being scheduled. And green is so every color is a different task, and that's it. We would like to have the least amount of white as possible, which means that we are using the resources better. So this is with 4,000, which is what Dask gives us as default. Let's go to something that we know is not going to be good. Let's put maybe 400. See how many we get now. Again, this one is declaration. It just should be fast. So now we have a lot of chunks. Let's compute here the mean. So declare here the mean and compute and see what happens. So now you see there is every task is divided by large scheduling times. So this is top now, but again it's Jupyter. And you can see the correspondence between colors here and the tasks. Okay, yeah, it's finished, but you couldn't see it because Jupyter stopped updating it. But anyway, you get the idea. So here it's very easy to see that for this size, this amount of chunks is way too much. And most of the time, if you compare the tasks, the colors with the whites, most of the time is just white. And so answering a question before that I commented in the chat. So this is one of the things that you can use to have an idea how much you're using in the graph itself, in scheduling, okay? All right. So sometimes so it's worth to maybe we can try here to make another example. Let's put less data and small chunks. So this is exactly the same thing, but with less data. So let's see what happens. This is a very little data. So if we comment here the chunks and we leave it automatically, Dask will tell us 2000 by 2000 array. This one you don't need Dask. This one is better to have only one chunk. And let's do it with Numpy. Only one thing. Okay. And this is something that it can be useful to when you are developing your scripts. And there is more. There is also the memory, but that one we can see it in the next in the example after the next. Okay, so now we close the IPython cluster. So now it's a Dask cluster. By the way, if here we pass Dask, and it's a Dask cluster, but also we can do we can do we still can do IPython calls with px. It's slow, and okay, sorry if you have time. But yeah, the px is still working. The IPython support still works in together with Dask. Okay, so we have only one node, so we are only seeing one more. So we can stop and move to the next one. Sorry. Okay, we can close here. Okay, it's ready. Let's move to the next. We'll restart the kernel. And let's move to the next one. So the next one, so we have only this one and another one to go, and we finish. This one is called Dask array from file. So this is a different kind of usage, but it's exactly the same backend and everything that we did. It's just a different use case. So now we were going to use H5Py because we have these 31 files, which in total is around I think around 16 gigabytes. But you can, if you have more, you can do it with many more. So each of these files has global weather data. I think it's the temperature. It's fake data, but it's the temperature for the average temperature for January, February, March, so on of 2014. Or I guess it's a day of the year or something like that. And so we have this data, and we want to compute the average temperature over the whole year. So we have temperature, global temperature per month, and we want the temperature per year. So let's see how we do it. So, H5Py is very convenient to work with Dask because you can connect NumPy arrays and then Dask arrays to H5Py files. And although this thing is taking a lot of time, this is very quick. So here at this point, we don't have any data being read. So we only use this to connect to the files. So we created a list of file objects, but nothing is read. Okay, so we can get the shape, but we don't have the data. So this one should be fast. I'm sorry about this. And now only when we plot it, when we ask for the data, do operations on it, like plotting, the data is going to be read. So here we are plotting the 0, so the January. And we are using this, which means read the data 8 by 8. Okay, so it's going to read the first element, then the 8th element, the 16th, and so on. So it looks like this. I think you can see here. So this is America, continent America, Australia around here. And this is, I guess, it's Africa, you can see, and Europe and the rest of the world. So this is the world, and there is the temperature value. And so we have 31 of this, and we want to get the average for every point over the year. Okay, so we're going to do that, to use Dask for that. So at this point, if we didn't plot, we haven't read anything. So we just connected these H5Py objects to the files, and then they behave like NumPy arrays if you call them, if you do operations on them. So now we are going to get from each of these objects, we are going to connect it to a Dask array. So, and again, we are declaring only here, and we're making a list of Dask arrays. So we have 31 Dask arrays, and we use Dask stack arrays, and we put them all together in a single array. So this one, again, doesn't take any time, shouldn't take any time. And yeah, so, and we want this shape. And this is exactly what we want. So the example I was saying before that we could see that sometimes we need to specify the chunks ourselves, can be an example like this one. Depending on the kind of operations that you want to do, maybe it's a good idea to tell Dask how to chunk. For instance, we have 31 here, and so one for each day in this direction. But let's say if this one is bigger, maybe we want to tell to Dask, okay, chunk only in this direction, in this way, and the other one, 31, leave it like that, and things like that. So this is, but this one now, Dask, the suggestion of Dask seems fine. We have 31 chunks, one for each month. So now the good thing of this, or one of the good things, is that we can operate, we can do operations, we can do this average that we want on the data with a single array. So we deal with it as it is a single array. It doesn't matter that we have many files. So if we were doing this one with NumPy, we would need to read all apart and combine them and do the combinations ourselves and loop over them. So in this case, we let Dask to do the work for us. And this one will work for 31 data files, and we work for for many more. It doesn't matter. We just put them there, and it will do the job. Also, if we use IPCMagick or we use the Dask cluster, we can the same thing. We can scale it over many nodes, and we're going to have a single array that is spanning over many compute nodes in a cluster. Okay, so we have this one, and so a single one. If we want to show it, again, this is fast. Is one of those. We can visualize it, of course. Okay, so at this point there is nothing being computed, although it looks like things being computed, but nothing is computed. So we define here an operation. So we are getting the average for every point in the plot in this direction over the 31. Sorry, I think I explained it completely wrong. So this is everything is January, and it's the 31 days of January. I'm sorry, that's why we have 31 here over the days. So it's a month. We're getting the average over a month. So we got mean, and now this mean that is just so we can put it here. Is now this one was fast. Is just a Dask array. There is nothing compute, and we can visualize if we want. So it's something like this. So these are the chunks. So this one should be, I guess, 31, and they are combining different operations. So they are a stack. I guess they put together, get the mean of a chunk, and then mean combine and mean combine partial. And this one should be yeah, aggregate. So very similar to the thing we saw before, but now instead of coming from a random, it will come from a file. And now we can pass this Dask array directly to matplotlib if you want to plot. And let's say that we want us to visualize and not to see the value. And matplotlib will operate on it, and Dask knows that it has to compute the array in order to matplotlib do the operation. So here we have another operation. We have the mean, so one of the days minus the mean, but we're not going to do it because it's very slow today. So this one is it should take around 30 seconds. Okay, and that's it. So now if you do IPCMagick and run over multiple nodes, this same code is going to run over multiple nodes. Okay, and this is going to be our example. So our last example. So let's go to the last notebook. So in the last notebook, we are going to use multiple nodes. We're going to use 2 nodes. I told you that maybe it was better to that I will tell you now better instead of before to change to a multiple notebook. Sorry, multiple nodes notebook. But I think it's better if you don't change, and maybe you can play with it in the afternoon, because since Jupyter is a bit slow, maybe you will end up locked out. So you can do this one if you have in a single node. I will do it in 2 nodes. I have 2 nodes here. So in this one, we're going to create a Dask cluster over 2 nodes, and I'm going to be using 12 workers, and I put 6 workers in. It is putting 6 workers in each node. So we have the thing. This one shouldn't be here, because IPyCluster creates a new one. And yeah, we can do what we did before. Let's see if now it wants to work faster. No, it doesn't. Otherwise, we can visualize the, okay, it's there. We can visualize the dashboard here. So what we are going to do here is to do an operation that requires a lot of computing, a lot of memory with this array. This is a silly operation. We are going to get the average of this array, and this array is 1.82 terabytes of data. So this is way more than a compute node. And the idea is that we're going to see here how Dask can compute this very easily. Just to make it a bit faster, we are going to read the data by 2, so every second component element. So let's put some visualizations here. So we're going to do, maybe we can show GPU memory. And there is this one, is kind of fun to watch, and it's quite illustrative. It's cluster map. It's not working, I think. Okay. So you see, this is the scheduler, and these are the workers, the 12 workers. And maybe we can do the, instead of a task string this time, to do not abuse Jupyter, we can show the graph. So we put the graph here. And this one, we put it here. So we have cluster memory. Maybe the memory and the graph, we can alternate over it. So if we do this terabyte of data, we can do it. It's a minute just for fun, but the graph is going to say that there are too many operations, so we better look at the memory. So we also have memory here, but this memory is the memory in the notebook. Things that happen in the cluster, they are not going to appear here. So we have this 1 terabyte of data, and we're going to do a compute of the mean. This is going to give you one number. So here we use the chunks as a million points as Dask leave them, and here it looks like we lost a worker, and it looks like it's not working very well, the dashboard, but it's too easy. So the memory is not showing the updates. So let's see if I can restart it. No, I'm sorry. So here you would see how the memory increases. Let's see if here this one is working. Although this link is being rerouted through Jupyter, so probably it's going to be a bit slow too. So yeah, we lost the whole thing. Yeah, this one is quite interesting because okay, let's see if the memory is working. No, it's not. You can see which workers are running, and then eventually you can see how the communication between workers happens, and it's very I like it very much because you get a very good idea on how the computation works, and it finished. So you saw all these lines at the beginning, and the cluster changing colors is corresponding to the different operations, and then at the end the red is the communication. Okay, let's put something smaller and try to see if it wants to show the graph. So now we have 74 gigabytes. And here, we see the graph, how it happens very quickly. But you can see how the memory is allocated and then emptied afterwards. Let's see if it's 200, we still can see and it lasts more. No, it has too many tasks to display. Let's see if the memory appears. No, the memory is like, doesn't want to show the memory. Here is showing. Yeah, it's the other one. So here we see the bytes stored and the progress, which is very slow. And we should see that after the thing finishes, the bytes store decrease a lot. And Dask always keeps a cache. That doesn't mean that it's going to explode, but it always keeps a cache, and I assume that it will delete it as it needs. I have never arrived to the point that it goes out of memory. Okay, and here we see the points that there is little this white thing, white spaces. I don't think they are accurate. I think this is just the way it's not painted well. And here we see a very little white spaces. And here at the end we see the red, which the red is the communication. So the communication is happening at the end, and at the end there is a lot of scheduling time lost because of the communication. But I guess it's fine, since it's not happening in the whole graph. If we put something, this is just doing it that already passed. It was just updated. If we put something like we force, let's put something small, like 50, and let's see how many chunks, 256, 300. So let's put again here less chunks, sorry, more chunks. So this is 100, 500, maybe, yeah, 500 by 500. Get 10,000 chunks, maybe this is too much. Okay, so let's compute. And let's go to the dashboard and see if it wants to work. And I think now maybe we should see more white spaces. Well, we don't see anything. Okay. So the whole thing passed and we couldn't see it, but in principle you should see spaces. Okay, I'm sorry about this because this has a bit of made the demos a bit not too good, but okay. So okay, so we are about to finish. This is the final thing. This Dask, there are different ways of computing it. So there is the compute that compute if you go to the documentation, for me at least, I find conflicting information, because they say that compute gives you a future, and a future is a concept that comes from the asynchronous execution world, let's say, and a future is an operation that it hasn't finished yet. So it's an operation that can be running right now and it's pending, and you don't have the final value, or an operation that it hasn't started yet, that you need to start. And with compute, always in practice, what it gives you is a value that is not part of the array, is of the graph. In this case, it will give you a number. So if you put type here, is a NumPy float, and this one if you run it, and in this case it's a number, but if you do a different operation, like let's say instead of min, you do something like this, result equal this thing times or square, and then you do compute. This will give you a NumPy array, so a non-Dask object. So it's an external object, and this object is going to be in the memory. So the memory you see here, in the memory of the notebook, and it's not going to be. It's not in the memory of the Dask graph itself. So this is something that is going to come out, and if you are operating over like here gigabytes of terabytes of data, or gigabytes, because if it is 70 is bad enough, this memory is going to come outside of the Dask graph, and it's going to blow up the memory of your system. Okay, so this is what compute does. It will give you let's call it the final result. It will give you an NumPy array, a number, something external to the graph. There is another way of doing it, which is called persist. Okay, let's just I will put this one to just to make it very quick. So persist is better. Persist is going to execute until the highest level of the graph. So in this case, we did this operation. So we square it, and the graph looks like this. So if we have more memory than what we have in our RAM in the system, this and we do it with compute, this memory is going to be filled, and we will get an out of memory error. And in this case, if we have the memory in the cluster somewhere else, this memory will never come to us. So let's say that we have a different setup here, not the actual one that I have. Let's say that I have a node where the notebook is running, or your script is running. So this is where the scheduler is running, and we have all these workers in different nodes, and we have, so this is 12 nodes. Let's say that we have 120 gigabytes of memory of data, and we do exactly the same operation. So if we do persist, this 120 gigabytes are going to stay distributed in the nodes, and here in the scheduler it never comes to your computer. Okay, and which we have 64 gigabytes. If we were to do compute, this 120, you are calling it to the we will be calling it to the node that we are, and it's going to, the memory is not going to be enough. And with persist you can do that, and also with persist, what you get is a future. So remember that here with compute we got a NumPy float, and here with persist we get a Dask array. So this result is still part of the graph, and it hasn't been brought to the notebook, to the script. Okay, so it's the numbers, the memories in the cluster. Of course, in reality, the way I set up the cluster is 2 nodes and 6 workers per node, and the notebook is one of these nodes, so the memory is still being used. But if you have a different setup where your the master node, where the scheduler is independent of the cluster, then this thing it will help you to have memory without around the cluster, without being on the notebook. And here there is something that we can do. We can do import Dask. No, sorry. From Dask import future of cannot include future of from Dask array. How is that? I'm sorry. From Dask import. What's it called? Just a second. I'm sorry, you have to. I don't know what is happening, or I forgot, or something's happening strange with Jupyter. Future of. So I'm just looking in a browser. Sorry, I think I didn't dream it. I will go. I will come back to you later. I think I forgot the name of the function. But I'm sorry about that. But yeah, you can see with that this one will return immediately. And you can see which one of, you can see all the dependency of it in a list. So you will see this size, it's 25 chunks, the 25 dependencies of it, and you will see a status. You can see that they are pending or they are already finished. And then after doing persist, if you do compute, which I won't do here because of memory. No, I can do it. We have a small array. This thing should execute quickly because the calculation is already done. Okay, and yeah, I come back to you in the chat with the example of the Dask of the future of, and that's it. And I think this is all I wanted to show you about Dask. If you have any questions, I'm sorry about the future thing, and the notebook has been a bit slow and it's a bit hard to understand what is computing and what is not. But I hope you could anyway get an idea of how this thing works.
There's a question on the chat.
Sorry?
There's a question on the chat.
Thank you, I didn't see it. Is it possible to see the GPU execution times just like the CPU execution time? Sorry, I don't understand the question.
I just wanted to know if you can see how long it took for the GPU as well. Like when you do the time, it shows how long it takes for the CPU.
Sorry, I think I did something here that may, I don't know if you get confused because I click here, that's why it wasn't showing anything. Sorry, I meant to use memory and processing. GPU memory, no, it's not GPU memory. Sorry, I meant to use CPU memory, which I don't find here now. I guess it's this one probably. But yeah, I dragged GPU memory, but that was my mistake. I clicked there by mistake. We are not using GPUs. Is that the question?
But if we were using the GPU, is it possible to see how long it takes you on the GPU, like on the Jupyter cell? When you use the time it function, it only shows the CPU, not the GPU.
I think that one it would be like what Theo showed yesterday, that in the CPU, if there are things asynchronous happening, then it can happen that this time that we do here, it will finish, so it will return before the whole thing is finished. Is it right? That's right, Theo, right? And the way to measure it would be as yesterday, as Theo showed. But I don't know if I am answering to your question.
Yeah, the best way to measure it would be to use, you might need to use the events from the events stuff from CUDA to measure.
Okay.
Okay. Okay, then this is it. This is the end of the of today and the end of the course. I hope it was useful to you, and you are going to start writing fast code on Python with everything that you learned. And the important things between with all the things that you saw today, there are many solutions. I think something very important is to always to know when to optimize your code. Maybe a good idea is to start with a simple implementation in NumPy that it should be good enough for many tasks. Moreover, if they are not too time consuming and too large, and from them try to see if you need maybe to offload some things to C, or maybe you need to use it with Numba, or maybe the best way is to use it on the GPU. And then after you have a very good implementation of your things, you may need to go and replace it with code, with delayed code of Dask to go through to use the whole, well, not the whole cluster, but to use many nodes in a cluster. And yeah, and there is something you would like to say there?
Oh, I would like to thank you for participating to the course. And if you have any questions, feel free to ask us. Also, you can find all the material more or less on the GitHub repository, and we have also more stuff there that we haven't presented, haven't had the time. So feel free to see there and take a look and replicate for yourself what we have done. So our purpose was more or less to show you what is available in the Python world when you want to accelerate your code, and therefore you can select what is best, what works best for your situation.
Yeah, there's a question. The recordings are going to be in. We'll put a link now in the webpage of CSCS. If you lose the link anyway, it's in tutorials, and there it should appear in maybe within a week or two. And yeah, so for the rest of the day, you have the accounts. You can still play in the afternoon. If you have questions, I think we both of us will be in the chat. And just remember, if you want to keep something from that you changed in the notebooks, copy it before the end of the day to your account or to your laptop, because the accounts are going to be disabled in the afternoon. Okay. And then with that, yeah, I would like to thank you very much for coming and being all these 3 days with us. And yeah, thank you very much.